Hello, physics. Yesterday, we pushed one student down the hall quickly at different speeds, actually, and we tried to take data points along the wall to mark where the path of this ball was that she threw up in the air. We noted that it made a certain shape. It made the shape of a full parabola. Before, we were talking about projectiles that were being launched horizontally and that they were a partial parabola, just half of one. Now, when one is launched from the ground and it moves forward and then hits the ground again, it makes a full parabola. So the trajectory again is talking about its path. We made several path points or data points on the wall, and we found that it made the shape of a parabola for a projectile. And so let's go ahead and look at some crazy, somewhat similar drawings of it. I have a spot on there where you should draw what the projectiles looked like when she was tossing it. And so we got some things that look like that. By the way, if we will be looking at this YouTube video, it's of how to get your high jump higher and making yourself a projectile, and we'll be watching that in class tomorrow too. Anyway, those drawings right there were similar to what we had when she was tossing the ball up in the air, and they are all parabolas. We have to look at these type of parabolas in a certain way. We can only look at them from two different points. Either you start from the bottom and go up to the top, where it stops up here at the top, or it goes and you catch it down here. These two speeds should be identical. It's one, except for that one is going in the positive direction and one is going in a negative direction. So we have to take this apart. We can't use the whole parabola as information. We have to take it apart so our math is actually capable of solving these problems. So we will take this information and we will either start down here with a velocity and we'll come up to a stop, or we will use the other side of the information. Like this would be perfect for solving an equation where you're taking off and you've got initial velocity and you come down this way. So there are two different ways to do it, but this is the easiest way to do it is with the formulas that I gave you to help us figure this out, because you've got to just use one part of the parabola to be able to solve any of your problems. So what are some other projectiles that look the same? Here's another one that's being launched at an angle. But to understand and be able to do our math, we have to remember how to do our trig. So here's some trig functions. I think you guys have got this on your formula sheet, but here's another one. I like it because these are the ones that we use actually in math all the time. And I've written them on the next page here with our abbreviations. So, ka, toa, remember that? Ka, toa. Helps us remember what order that they go, and that when you're talking about a right triangle, here's our right angle. The hypotenuse is across from it, but the angle that we are analyzing, the opposite side is not touching that angle, and the adjacent side is touching that angle and is not the hypotenuse. So we can use this setup here to help us solve many problems in trig. And so like if we had that this was a 3, 4, 5 triangle, we could look at it and we could figure out what would be theta. So the sine, we'll use a sine because we've got a 3 over here and we've got the hypotenuse, okay? And we've got 3 over 5 because it's the opposite over the hypotenuse for sine. And so you can't just solve it by the sine of theta equals 3/5. You have to do the arc sine of it, and or the inverse sine of it, and then you should get that the angle is about 36.8 degrees. And so this is our typical triangle that we use so often in science. And you also note that you can use the Pythagorean's theorem to solve many of our problems too, to find out how long that this hypotenuse would be, or else any of the other sides. Okay, for our purposes, most of the projectiles we're solving for C. We're solving for the hypotenuse, but we could do it other ways too. Okay, so let's look at some other trig functions here. We've got some motion going on. In this first section right here, here's an airplane that is flying forward at 80 kilometers per hour, and it is going forward, and it has a tailwind of 20 kilometers per hour, and so this is nice. We get it. You got 80 kilometers per hour. You're adding 20 more kilometers per hour, and so you get a total speed of 100 kilometers per hour. But that's not good enough. You've also got to put what direction, because velocity, remember, is always a vector, and vectors you have to use direction. Okay, here's another plane. It's flying the same speed, 80 kilometers per hour, and it is against a headwind of 20 kilometers per hour. So it's not going near as fast. In fact, it's going 60 kilometers per hour. 80 minus 20 gives you 60 kilometers per hour, but it's still going north. And of course, we have to write that down when we are talking about vectors. Anyway, here's another plane again, 80 kilometers per hour, but it's got a crosswind, and we're going to say it's to the right or it's to the east. I guess it'd be the west. And anyway, so here it is, and we've got 60 kilometers per hour wind right here. Okay, and moving on, we want to worry about that hypotenuse that we're going to draw on it. Excuse me. And here's the hypotenuse. You can take that 60 mile per hour, put it up here, make your triangle. Okay, and so you can see where it's going to go. And we need to find its resultant. So that means that we need to find this length here, and we need to also find theta. Okay, so let's do that. There's the resultant there. And yeah, I know this is a 3, 4, 5 triangle. I was trying to make it easy. So 3 times 20 is 60. Oh, goodness. And let me get back there. And 3 times 4 is 8. Excuse me. 3 times 20 is 60. 4 times 20 is 80. And 5 times 20 is 100. And so we knew that that was 100 kilometers per hour. But if it was not that nice of numbers, you could have used your Pythagorean's theorem to figure that one's length out. So it's 100 kilometers per hour, but what is that length? Okay, and let's just practice the math, even though we probably know what it is. Let's look at it. We know that we've got an opposite. We know we've got an adjacent, so we need to use tangent. Okay, opposite over adjacent, so that's going to be the 60 over the 80. Okay, we'll use our arctangent or else our inverse tangent, and we'll get 36.8 degrees. Now, how do we report that? I mean, you could report it from north from the east, or east from the north. And why am I saying east? This should be west. Sorry. Anyway, so you would report it as 100 kilometers per hour, 36.8 degrees east of the original north direction. Okay, let's talk about this in other terms too. Here's a sample problem. We're going to come up with the x and y components of this. Okay, a football is thrown at a speed of 20 meters per second at an angle of 30 degrees with respect to the horizontal. Okay, so let's first of all draw a picture of it. We want to find the horizontal velocity, and we want to find the vertical velocity. So let's draw a picture. Okay, it's going 20 meters per second, and it's at 30 degrees. Okay, we've got and that's with the horizontal there that we're talking about. So we can figure out the horizontal velocity. Okay, since this is in meters per second, that's telling us that our answer will be in meters per second. So it's not finding a distance, it's finding a velocity. Anyway, so let's go ahead and solve this. That's an adjacent. X is on the adjacent side of it. So we will say, so we'll solve for it this way. Cosine equals adjacent over hypotenuse. The cosine of 30 degrees is going to equal x, which is our direction we're talking about, velocity in the x direction, over 20. Okay. This is nothing new for us, right? This should be reminding you of things you do know from the last unit. And it's easier if you plug it in the calculator as 20 times cosine of 30. Sometimes we don't put it in the calculator correctly, and we get the wrong result. So I advise you to stick it in the calculator this way. And you get out of that 17.3 meters per second. Okay, that's pretty nice. We'll be using that answer for the next problem too, for the third one on this one. Anyway, here's our drawing again, but this time we're going to solve for y because we want velocity in the y direction, and that's the opposite side of the 30-degree angle, so we will have to use the sign, opposite over hypotenuse. And that is the sine of 30 degrees over the opposite side, which is y in this case because it's going upwards, and over 20, which is the hypotenuse. And so for that one, we'll take 20 times the sine of 30, and we will get 10 meters per second. That isn't good enough, though, because we need to have 3 significant figures. Remember that? So it'll have to be 10.0 meters per second. Anyway, that is our horizontal and our vertical velocity components of a football thrown at 30 degrees at 20 miles per hour. Now let's just use that same exact situation here, but now we want to say in this case the football is thrown. We've got things figured out, but we want to know what the range is. Okay, and so we've got one formula. We know that the distance or else the displacement equals the velocity, in this case the x direction, because we're trying to find out the whole distance of x, times time. And we want to know how it's going to do that in 3 seconds. So we figured that on the other page. We figured out that it was 17.3. Oh goodness, I've erased something here. We figured out that it was 17.3 meters per second, and they want to know how far it'll be in 3 seconds. So it will be times 3 seconds, and we will get 519 meters. Okay, just a reminder, you didn't have to worry about the vertical speeds at all with that because we were talking about the range, and you have to chop up all the different projectile information and just use either the vertical components or else the horizontal components. You can figure out one to use for the other, and that's nice too. Okay, we will stop here and talk about these tomorrow.